Welcome to an exploration of one of the most profound and challenging problems in mathematics, the Riemann hypothesis. It's not just any problem. It's a Clay Institute Millennium Problem, which means that there is a $1 million prize for anyone who can either prove it or disprove it. So, what exactly is the Riemann hypothesis? At its core, it is a conjecture, a mathematical statement that is believed to be true but has not yet been proven, about the distribution of prime numbers. Prime numbers, those numbers divisible only by 1 in themselves like 2, 3, 5, 7, and so on, are fundamental building blocks in number theory. This hypothesis was first proposed by Bernhard Riemann in 1859, making it a long-standing and deeply intriguing problem. The Riemann hypothesis is intimately connected to the Riemann Zeta function, denoted as zeta of S. This function is defined by the infinite sum shown on the screen. Zeta of S equals the sum from n equals 1 to infinity of 1 divided by n to the power of S. Here, S is not just any number but a complex number. Complex numbers have a real part and an imaginary part, and they open up a whole new dimension in the study of numbers. The Riemann hypothesis makes a very specific claim about where the non-trivial zeros of the zeta function lie. These zeros are values of S for which the zeta function equals 0. The hypothesis states that all of these non-trivial zeros lie on what is called the critical line. This line is defined by the equation S equals 1/2 plus I times t, where I is the imaginary unit, the square root of -1, and t is any real number. In simpler terms, the real part of these complex zeros is always 1/2. The Riemann zeta function might seem abstract, but it has a surprising and deep connection to prime numbers. Euler's product formula establishes this connection, linking zeta of S to all prime numbers through the equation. Zeta of S equals the product over all prime numbers p of 1 divided by 1 minus p to the power of -s. This formula reveals that the zeta function encodes information about the distribution of prime numbers. To understand the distribution of prime numbers, mathematicians use the prime counting function, denoted as pi of x. This function counts the number of prime numbers less than or equal to x. The Riemann hypothesis, if true, provides precise bounds on how prime numbers are distributed. Knowing these bounds allows mathematicians to make accurate predictions and understand the patterns in the seemingly random sequence of prime numbers. Despite being unsolved for over 150 years, significant progress has been made in verifying the Riemann hypothesis. As of now, the first 10 trillion zeros of the Riemann zeta function have been checked and found to lie on the critical line, providing strong numerical evidence for the hypothesis. The Riemann hypothesis is not just an abstract mathematical problem. Its solution has far-reaching consequences. Understanding the distribution of prime numbers has profound impacts on cryptography, the science of secure communication, quantum computing, and pure mathematics. A proof of the Riemann hypothesis could unlock new breakthroughs in these fields. The Clay Mathematics Institute has designated the Riemann hypothesis as one of the 7 Millennium Problems. A correct proof or disproof of the hypothesis will not only earn the solver a place in mathematical history, but also a $1 million prize. The Riemann hypothesis remains the greatest mystery in mathematics, captivating mathematicians and scientists around the world. The question remains, will you be the one to solve it? The journey continues, and the opportunity awaits. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.